Hello, welcome to my video lecture. In this video I want to describe the behavior of spins in magnetic field. To be more specific, I will consider the spin states of an ensemble of isolated spin 1/2 particles. Also I will take the magnetic field consisting of two parts. The first one, which I orient along the z-axis, is strong and stationary, and the second one, is small and fast oscillating in the direction orthogonal to the first one. Probably, if you are familiar a little bit with magnetic resonance, you have recognized that this is a typical situation when a pulse is applied to a spin system. Here, my goal is to introduce the basic theoretical approaches to predict the dynamics of spin magnetization during radio frequency or microwave pulses. Okay, let us start with a simple Hamiltonian describing interaction of the magnetic moment, mu, with the magnetic field, B, which is simply the product of both with minus. The magnetic moment vector operator, mu, is proportional to the vector spin operator consisting of the three components, Sx, Sy, and Sz. Gamma is the gyromagnetic ratio, and h bar is the Planck constant. In our case, the magnetic field vector, B, which in general can depend on time and coordinate, is given by the components shown in the figure. By inserting our expressions for mu and B into the Hamiltonian, we transform it into a more explicit form. Now I will specify magnetic fields even more. The stationary part, which usually should be made homogeneous for high precision measurements, has often small deviation from some central value, B0, throughout the sample. Therefore, we present the stationary field B longitudinal as B0 plus some delta B of R, which can be approximated via the product of the field gradient G and vector R, which is much smaller than B0. The transversal field is assumed to be harmonically oscillating with the frequency omega and magnitude denoted by B1, which is much smaller than B0. Also we assume that B1 is switched on at time point 0, that is reflected by this relation. With this I obtain the following Hamiltonian. It can be rewritten as a sum of three terms, H0, delta H and H irradiation. The first two, H0, and delta H, denote spin interaction with the stationary field, and the third term, H irradiation, corresponds to the spin interaction with the oscillating B1 field. Since I want to compute the evolution of the spin magnetization, I need to know its initial value before the first pulse is applied. I assume that at the beginning the magnetization has its thermal equilibrium value, which can be determined from the density matrix of the spin system. This matrix can be obtained via the known formula, ρ equilibrium is equal to e to the power of minus beta h, divided by the trace of e to the power of minus beta h. Here, h is the Hamiltonian, and beta is the inverse value of the Boltzmann constant multiplied by the temperature T. With a good precision, I can use the H0 instead of the full Hamiltonian in this density matrix formula, because H irradiation is not acting until time 0, and delta H can be neglected because it is much smaller than H0. By inserting H0 into our exponential function, I obtain the following. Here, I have introduced the variable omega 0, which is minus gamma B0, and the Pauli matrix sigma z, which is proportional to the spin projection operator Sz. Now I will show how the exponential matrix with the argument proportional to the Pauli matrix, sigma z, can be calculated explicitly. For this, I will perform a serial expansion. Taking into account that the sigma z squared is equal to a 2 by 2 unit matrix, I can converge our seria to the two terms. The first is hyperbolic cosine of beta h bar omega 0 divided by 2, and the second is the sigma z multiplied by hyperbolic sine. By inserting this expression into the density matrix, I obtain immediately Majority of magnetic resonance experiments are performed in so-called high-temperature limit, that is, when Boltzmann energy kBT is much larger than the spin interaction energy, or Hamiltonian H0. For example, if we take the room temperature, or lower, let's say 100 K, then the Boltzmann energy is on the order of 10 to the power of minus 21 joule. Now, even for very high magnetic resonance frequency of 100 gigaradian per second, the energy splitting between the spin states is on the order of 10 to the power of minus 23, which is much smaller than the Boltzmann energy. This allows me to use beta h bar omega 0 divided by 2, instead of sine from the beta h bar omega 0 divided by 2, and 1 instead of cosine function. Taking into account that the trace of a unit 2 by 2 matrix is equal to 2, and the trace of sigma z is equal to 0, I obtain ρ equilibrium is equal to 1/2, multiplied by 1, minus, sigma z multiplied by beta h bar omega 0 divided by 2. In fact, the first term, the unit matrix, does not play a significant role in further computation, therefore it is omitted. Hence, we can proceed further with a reduced density matrix, which can be written as follows. Now I can derive the initial thermal equilibrium spin magnetization from the obtained density matrix. For this, I need to calculate the trace of the density matrix multiplied by the magnetic moment operator and multiply the result by the spin concentration. In this formula I am inserting the expressions for mu and ρ, derived above. Hence, I obtain for the m equilibrium vector, nc gamma h bar, multiplied by the vector with the three components, trace szsx, trace szsy, trace sz squared. Since the trace szsx and the trace szsy are 0, and the trace sz squared is 1/2, I obtain the initial magnetization vector in the form, nc gamma h bar, multiplied with the vector with the only one non-zero z component. Using the formula for the coefficient, c, and omega 0, I can express this z component of the equilibrium magnetization, or the absolute value of the initial magnetization vector, via the constants, h bar, kb, gamma, and the concentration, n, temperature, T, and magnetic field, B0. Summarizing this part, I can say that I have derived the initial thermal equilibrium spin magnetization, its absolute value, and its orientation along the magnetic field B0. Okay, let us move on to the period when the pulse is switched on. It means that beside the stationary field B0, the spins are affected by a harmonically oscillating field B1. In this case, I need to determine the density matrix, which is driven out of the equilibrium by the irradiation. As it is well known, the time evolution of the density matrix is determined by the Lyoville, von Neumann equation. Here, I would recommend to watch my another video, discussing its usage in magnetic resonance. The video is called Description of Magnetic Moment Motion. Okay, the Lyoville, von Neumann equation has a form similar to Schrödinger equation, wherein I should use our Hamiltonian with the time-dependent cosine omega t function. Here, I have introduced two variables, delta omega, and omega 1, similar to omega 0 above. Remarkably, omega 1 is proportional to b1 divided by 2. The reason for such definition will become clear later. Now we need to solve this equation. For this purpose, I will use unitary transformations frequently. In other words, I will introduce a unitary operator, R, and the corresponding density matrix, ρ'. The ρ, and the ρ' are linked via the formula, ρ is equal to inverse R, ρ', R. By inserting such ρ into the Lyoville, von Neumann equation and performing some transformations, I obtain a very similar equation for rho prime. The only difference that I have some effective Hamiltonian HE instead of H. Here, HE is defined as R, H, inverse R, plus I, R time derivative, multiplied by the inverse R. To get the last term, I used the relation, that R, multiplied by the inverse, R, is equal to constant unit matrix, the time derivative of which is equal to 0. Okay, let me specify the operator R. I will choose it as e to the power of I omega, t, sz, which corresponds to the rewriting the spin Hamiltonian in the frame rotating with the angular frequency, omega. Inserting R into this formula, I obtain the following result, wherein Sxt is the so-called sandwich operator of Sx. The obtained Hamiltonian can be simplified. First of all, we will choose omega equal to omega 0, or we tune the irradiation frequency to the Larmor frequency of the spins. Further, I will write the sandwich operator, Sxt, in the explicit form. This result for Sxt can be obtained by a direct but somewhat lengthy matrix multiplications, which I don't want to comment here. However, I would like to point out an interesting feature, which can provide us with some intuition how to calculate such kind of sandwich operators. We see that the action of the exponential, I omega t, sz, from the left, and the exponential, minus I omega t, sz, from the right, on the spin projection operator Sx, resulted in the spin projection operator, Sx, and Sy, with the prefactors, cosine omega t, and minus sine omega t, respectively. Very similar happens, when we have a unit vector along the x-axis of a coordinate frame, and rotate it by angle minus omega t. We obtain a vector with x projection, cosine omega t, and y projection, minus sine omega t. Hence, calculation of sandwich operators can be deduced from the corresponding unit vector rotations. Okay, let us go back to our Hamiltonian, that I obtained. The last term, proportional to omega 1, is oscillating, however, it has a constant component. I will extract it by the transformation of the trigonometric functions products via the Euler-Hilary formulas. With this, I obtain He, which has two constant terms, and one fast oscillating term with the time averaged value equal to 0, which can be neglected. Hence, I am left with the Hamiltonian consisting of two constant terms, delta omega sz, and omega 1 sx. This Hamiltonian can be inserted into the Lyoville von Neumann equation. Its solution can be given by the sandwich operator of the initial density matrix, rho prime of 0. The rho prime of 0 can be determined using the formula relating rho prime and rho, shown above. It yields. With this, it can be easily shown that rho prime of 0 is equal to rho equilibrium, that is, CSZ. Okay, in order to solve this equation, I need to make another trick. I will introduce another unitary transformation via the operator, r bar, equal to e, to the power of I, phi, sy. The angle phi is defined in such way, that tangent phi, is equal to delta omega, divided by omega 1. The inverse r is determined straightforward. Now, I make a statement, the unitary transformation of He simplifies our Hamiltonian just to one term, proportional to Sx, with the coefficient, capital Omega, defined as the absolute value of the sum of vectors delta omega and omega 1. The transformed Hamiltonian is denoted as He prime. Furthermore, it can be shown that the inverse R bar, e to the power, minus IHET, R bar, can also be written in a simple form, e to the power, minus IHE prime, t. Now, I can use these relations in the solution of the Lyoville von Neumann equation. Since R bar, multiplied by the inverse, R bar, is equal to 1, I can rewrite the last expression as basically, I have inserted here, at for positions, unit matrices. Now, I can substitute these parts of the expression with this formula, that yields. Here, I have rho double prime of 0, in the middle, which is defined as rho double prime is equal to, inverse R bar, multiplied by rho prime, multiplied by R bar. By inserting here the expressions for the rho prime, and R bar, which were shown above in this video, I obtain another sandwich operator, which can be calculated by analogy with the rotation around y-axis, of a unit z-axis vector. This gives me the density matrix with Sz and Sx components. Okay, we have expression for rho prime of t, He prime, and rho double prime of 0. Now, I will insert He prime, and rho double prime of 0, into the expression for the rho prime of t. This gives me the following expression. I will start with the calculation of this part. First of all, the second term will not be changed by the multiplication with the exponential operators from the left and from the right. The first term can be calculated, if I take into account that the sandwich operator of Sz is given by this formula. Hence, I obtain the following expression. For a convenience, here, I will add and subtract the term, Sz cosine phi, in the following way. Now, let me remind, that this term is equal to the inverse R bar, Sz, R bar. With this, I obtain by calculating the last sandwich operator, I can write the following result for the density matrix, which has terms, proportional to Sx, Sy, and Sz. So, we have the density matrix time evolution for a system of isolated spins 1/2, under the action of harmonically oscillating magnetic field, B1. As explained above, this density matrix describes the system in the rotating frame with the angular velocity, omega. Now, I can calculate the spin magnetization in the rotating frame. It is obtained as the concentration, n, multiplied by a trace of the density matrix multiplied by the spin magnetization operator, mu. Via simple direct calculation, I obtain the three components of the spin magnetization vector, mx prime, my prime, and mz prime. Here, a prime is a new constant factor. With this general result, I can consider several important cases. First of all, let us look at the case, when delta omega is 0. Then I get tangent phi, and consequently phi, equal to 0 also. Hence, the x component of the magnetization vanishes. The y and the z components start to oscillate with the same magnitude, A', and the same frequency, omega 1. Note that frequency, capital omega, is equal to omega 1 in this case. Now, let us consider another extreme case, when delta omega is very large. Then, tangent phi is infinite, and phi is pi over 2. Consequently, mx prime and my prime are 0, and the z component, mz prime, remains equal to the initial spin magnetization value. In other words, nothing really happens when delta omega is large, that is, when we are far off resonance. So, we have analyzed the two extreme cases, summarized here. Now, let us look at an intermediate situation, when delta omega is equal to omega 1. In this case, tangent phi is 1, and cosine phi is equal to sine phi, and is equal to 1 over squared root of 2. With this, I obtain magnetization vector m prime, with the three components different from 0, and capital omega equal to squared root of 2, multiplied by omega 1. Okay, now, let me demonstrate the obtained results graphically. In the first case, the effective magnetic field, and frequency, capital omega, are oriented along the x-axis in the rotating frame. Hence, the magnetization rotates in the yz plane, with the angular velocity, capital omega, which is equal to omega 1, here. In the second case, delta omega is very large, and the effective rotating frequency, capital omega, goes along the z-axis. Therefore, the magnetization, which is initially oriented also along z-axis, rotates around z-axis. Obviously, in such situation, no effect is observed. In the third case, the vector, capital omega, is oriented along bisection between the x and z axes. Hence, the initial magnetization will move on the surface of the cone, shown in the figure. Now, let me estimate the time scale of the spin magnetization rotation for typical experimental situations. In the first case, we see that the magnetization is rotated by the angle alpha, equal to omega 1, t, during the time t. If we want to know, how long does it take to rotate the magnetization by angle pi, we need to calculate t from this simple formula. If I take B1 field about 1 millitesla, then the rotation time by angle pi will be on the scale of tens of nanoseconds for electron spins. For proton spins, I obtain rotation duration about 1000 times longer, that is, tens of microseconds. Now, let us investigate how the magnetization components depend on the frequency offset delta omega, which determines angle phi via the equation, tangent phi is equal to delta omega divided by omega 1. For convenience, I will introduce variable, x, equal to tangent phi. In order to make plots for mx, my, and mz, I will choose the time parameter, t, equal to pi over 2 omega 1. Now, I can rewrite my expressions, for the magnetization vector components, for the defined time, via variable x, as follows. This allows me to plot mx, my, and mz, as function of the variable, x. These figures illustrate the magnetization of the spin package, corresponding to the value, x, which is the ratio of delta omega to omega 1, after pi half pulse. Okay, here, I would like to finish my video lecture. Thank you for your attention, and please watch other videos in my channel, related to magnetic resonance. Bye bye.